Hello, welcome. We're glad you joined us. I'm Ilan Niska, Microsoft Technical Trainer. This course covers 6 sessions where learners will build a foundational understanding of core data concepts and how data is stored, processed, analyzed, and visualized in Microsoft Azure. In this session, we'll cover an introduction to relational data in Azure. So let's get started. Relational databases power everyday systems like orders, customers, and inventory. This session introduces the fundamentals of relational data and how it is used in Azure. We'll focus on core concepts and main Azure services. This session has 2 parts. First, we'll look at the core ideas behind relational data. Then we'll explore the Azure services that support relational databases. Here are the goals for this session. By the end, you will be able to recognize what relational data looks like, understand what normalization means, and identify the different types of SQL statements and database objects. You will also get familiar with Azure SQL options and open source database services, and we will demo provisioning a database in Azure. Relational databases are built on predictable structure. Tables work because every row flows the same shape, and that consistency is what business transactions depend on. With that idea in mind, we can look at how tables organize data and why that structure matters. Relational databases organize information into tables. Each table represents a collection of similar records, and every record follows the same layout. That consistency makes it easy for applications to store, retrieve, and reason about information. Each table usually represents a real-world entity, such as customer, product, or order, and each row is a single instance of that entity. Even when some values aren't available, the structure stays intact. For instance, a customer might not have a middle name, so a middle name column can remain empty without disrupting the rest of the row. The columns in the table define what kind of information the system expects to store. Each column has a data type, and that data type tells the database how to validate, sort, and operate what the values are in it. An email column, for instance, is stored as text because it consists of characters. The price column in a product uses a decimal number, which allows the system to calculate totals and averages accurately. A quantity column often uses an integer value, so it can count whole units, while an order date column will use dates or date and time data type, so the system can understand chronological order and time-based relationships. These data types help enforce accuracy and consistency. When an application inserts data, the database checks the values against these definitions to make sure they match the expected structure. Text goes into text columns, numbers into numerical columns, and dates into date columns. This is one of the core reasons relational systems are trusted in business applications. The structure ensures reliable and predictable behavior. Different databases engines support different sets of data types, but many are standardized by the American National Standards Institute, or ANSI. That standardization means that essential concepts remain the same across platforms, even though each system might add additional specialized types. What is consistent across all relational systems is the idea that data types describe the shape of the data and guide how it can be used. Understanding tables and data types is the foundation for everything else in a relational system. Once data is organized into well-defined structures, the database can help maintain quality, enforce rules, and support meaningful queries. Normalization is the way relational databases reduce duplication and keep data accurate as it grows and changes. The idea is simple. Instead of storing the same information over and over again in a single table, the database separates each kind of information into its own place and connects those pieces through relationships. This is how relational systems avoid inconsistencies and make sure that the data you query is reliable. Imagine a company tracking sales in a single spreadsheet. Every time a product sells, the product name and price are typed again. Every time a customer places an order, their name and address are copied again into another row. The spreadsheet works for a small amount of data, that you can immediately see the risk: a misspelled customer name in one row, an outdated address in another, or a product price recorded differently. If nothing forces the spreadsheet to remain consistent, repetition can grow quickly. A normalized database fixes this problem by storing each entity once and referencing it everywhere it's needed. Customer information goes into customer table, product information goes into a product table. Each row in those tables has a unique identifier, usually a primary key. An order no longer copies the customer name or address. Instead, it stores the customer's key value as a foreign key. If the customer moves or changes an email address, the update happens in one place, and every related order automatically shows the correct information. The same is true for products. The product name and price live in one main place where the information is stored, and every line item is in every order simply pumps back to it. When an order claims to reference a customer, the database can ensure that the customer exists. It prevents orders for non-existent products and helps guarantee that each relationship in the data is valid. By breaking data into related tables and making those relationships explicit, relational systems maintain accuracy, even as millions of records are added. The idea is to understand why relational databases separate information into multiple related tables. It minimizes repeated values, reduces inconsistent updates, and allows the system to protect the integrity of the data. Once these relationships are in place, the database can scale cleanly, query efficiently, and support analytics and applications with reliable, structured data. Let's talk about structured query language, or SQL. It is a standard language used by relational databases to describe, manage, and work with data. SQL provides a consistent way to define how data is structured, control who can access it, and interact with the rows stored in a database table. While each database vendor might add its own extensions, the core concept is the same. Across systems, the consistency is why SQL has been the foundation of relational databases for decades. At a high level, SQL statements fall into these broad categories, each with a clear defined role. Together, those categories form a simple but powerful model for managing data in relational databases. The first category is Data Definition Language, or DDL. DDL statements describe the structure of a database itself. They are used to create database objects, modify the design, or remove them when they are no longer needed. A common table is the create table statement, which defines a new table and its columns so the database knows how the information should be stored. In other words, DDL answers the question, what does the database look like? The second category is Data Control Language, or DCL. These statements focus on security and access control. Because databases often contain important or sensitive information, there must be a way for you to control who's allowed to read data, change it, or manage database objects. A grant statement gives a user permission to perform specific actions, while a revoke statement removes that permission. DCL ensures that only the right users and applications can work with specific data. The third category is Data Manipulation Language, or DML. DML statements work with the actual data stored inside tables. These are used to insert new rows, update existing values, delete data that is no longer needed, and retrieve information. A selected statement, for instance, reads data from a table and returns it in a structured result set. Because DML operates directly on table rows, it is central to applications, reports, and dashboards that rely on relational data. When viewed together, these three categories provide a complete and balanced approach to working with relational databases. DDL defines the structure, DCL controls and protects access, and DML operates on the stored values. Recognizing the role for each category makes SQL much easier to understand without needing to write queries. At a fundamental level, SQL serves as the common language that keeps relational systems predictable, secure, and consistent across technologies. This understanding gives us the foundation we need as we move to explore relational databases, objects, and how SQL is used across different Azure database services. In addition to tables, relational databases include several other objects that help applications work with data in a consistent and efficient way. These objects provide additional tools to structure queries, perform standard operations, and enhance the efficiency of information retrieval within the system. One of the most common objects is views. A view is a predefined SQL select query that functions as a virtual table. When you query a view, the database runs its select statement and returns the result as a table. This is useful because a view can bring together information from multiple related tables. Here's a view that joins orders and customers so you can easily see delivery information without repeating the join logic every time. Views make it easier for people and applications to work with data without needing to understand the structure or the database. They also help simplify access to normalized schema. Then we have stored procedures. There are pre-written SQL statements or a set of statements that run on demand. It can accept parameters, allowing you to input values for specific actions. For example, a procedure might update a product name. Stored procedures are helpful when the same data operation needs to be performed repeatedly, or when you want the logic to run inside the database engine for consistency. They provide a simple way for applications to request an operation without needing to rewrite the SQL each time. Then we have indexes. Indexes are the structure that improves queries speed by helping the database find specific rows quickly. Without an index, the system often needs to scan an entire table to locate a matching value. An index creates a tree-based structure organized by one or more columns, which allows the database to search in a more direct and efficient way. Here, product names are sorted alphabetically so that the engine can jump to the correct portion of the data. Indexes make data retrieval faster, especially in large tables. Together, views, stored procedures, and indexes show that relational database contains more than just tables. These objects help organize logic. Let's do a quick check before we start mapping them to Azure services. We have three questions. The first one is, which one of the following statements is a characteristic of a relational database? I'll give you some time to think. For the first question, the correct answer is that a row in a table represents a single instance of an entity. That's the core idea behind relational tables. Every row follows the same structure, and each row describes one customer, one product, or one order. Let's look at the second one. Which SQL statement is used to query tables and return data? For the second question, the SQL statement that returns data from a table is select. Structured query language uses select to read information from tables and return it as a result set. Let's look at the third one. What is an index? For the third question, an index is a structure that helps the database locate rows more quickly. Instead of scanning the entire table, the index organizes values in a way that allows the engine to jump directly to the matching rows. Now that we confirm those ideas, we can continue building on this foundation as we explore Azure relational databases services. Azure offers several managed services designed to store and work with relational data in the cloud. This part of the session focuses on the main options available and the roles they play in supporting structured workloads. Azure SQL refers to a family of relational databases services in Azure that are built on the Microsoft SQL Server engine. SQL Server has been one of the most widely used relational database management systems in the world, supporting mission-critical applications for decades. Because the Azure SQL servers are the same engine, organizations can bring existing workloads to the cloud with minimal changes or build new cloud-first applications that use familiar relational capabilities. One option in this family is SQL Server on Azure virtual machines. This offering runs a full instance of SQL Server inside an Azure virtual machine. This approach is ideal when exact compatibility with an existing on-premise SQL Server is needed. Administrators retain full control over the OS and SQL configuration just as if they would on their own data center, including patching, backups, and performance tuning. Costs are also driven by virtual machine usage and SQL Server license. Another option is to go for Azure SQL Managed Instance. This service provides a platform as a service, meaning that the platform automates most of the operational tasks that SQL Server normally requires. Managed Instance is highly compatible with on-premises SQL Server, enable easy cloud migration with minimal changes. You can run multiple databases with a managed instance or create a pool of instances that share the same resource limits, giving organizations flexibility as they consolidate or scale their workloads. Azure SQL Database is the most streamlined offering in the Azure SQL family. It is also a platform as a service option, and it focuses on low administrative overhead. The platform automatically handles maintenance, tasks behind the scenes, leaving administrators responsible mainly for the database schema and access controls. This service supports a single database model or an elastic pool, allowing multiple databases to share the same compute resources. It is an attractive choice for modern cloud applications that need cost-efficient relational store with built-in automation. Across these services, there is a clear progression in how much control and responsibility organizations take on. Running SQL Server on a virtual machine gives full control, but also requires full management and tends to be much more expensive option. Azure SQL Database sits on the other end of the spectrum with the lowest cost and the highest degree of built-in automation. Managed Instance sits between them, balancing compatibility, control, and operational efficiency. Together, these options allow teams to choose the level of flexibility or automation that best fits their relational data needs. Azure also includes managed services for some of the most widely used open source relational database engines. These services make it possible to run familiar technologies in the cloud while relying on Azure for high availability, monitoring, backups, and maintenance. Each service is built on the community edition of the underlying database engine. So the behaviors and capabilities match what developers already know while adding the benefits of a fully managed platform. One of the options available is Azure Database for MySQL. MySQL began as a simple and approachable open source database and over time became a core part of the LAMP application stack. LAMP stands for Linux, Apache, MySQL, and PHP. Many web applications have historically relied on this combination. Running MySQL as a managed service in Azure means organizations can bring those applications to the cloud without having to administer the database engine or manage updates. Another choice is Azure Database from MariaDB. MariaDB was developed by the original creators of MySQL. As a fully open source alternative, Although it builds on ideas from MySQL, the database engine has been reworked and optimized to improve performance. MariaDB generates significant interest due to its compatibility with Oracle database. Many applications written for MySQL can work with MariaDB with minimal changes, which creates a smooth path for teams using open source tools who want better performance or expanded features. Azure provides this database as a managed service, giving teams the same operational advantages as the other offerings in the family. Azure Database or PostgreSQL completes the set of open source relational engines supported in Azure. PostgreSQL has a reputation for reliability, standards, compliancy, and rich feature set that appeals to developers and data engineers. It blends relational storage with the ability to define custom data types and work with non-relational concepts, which gives it flexibility beyond traditional table-based designs. PostgreSQL is often called just Postgres. The name comes from the older research database called Ingress. Postgres literally means post ingress. Later, when full SQL support was added, the project became PostgreSQL. You don't need to remember any of that for the exam, but it explains the name you'll see everywhere. Running PostgreSQL in Azure offers the same convenience as other services. Patches, updates, and maintenance tasks are handled by the platform, so teams can focus on application logic and data design. Together, these open source database services make it possible for organizations to use the technologies that align with their existing applications, developer skill sets, or architectural preferences. Whether an application was originally developed on LAMP stack, built using Oracle-compatible logic, or designed to take advantage of PostgreSQL extensibility, Azure provides a managed option that brings each engine strengths forward into the cloud. We'll go over the demo. We're going to walk you through the process of creating Azure SQL Database and then exploring it using simple SQL queries. The goal is to help you see how a managed relational database behaves in Azure. We will create AdventureWorks sample database, which will give us a realistic set of tables and rows to experiment with. Let's open the portal in Edge. We need to go to portal.azure.com. We need to authenticate. Once we're in, we need to go to Azure SQL. And when you are in Azure SQL, you'll note that you're not going to a resource right away. You have options: SQL Database, Managed Instance, SQL Server. Let's compare the options. You can see more detail here. Some of them are platform as a service, and a virtual machine is infrastructure as a service. You have more details also to compare: cloud native applications, migrations, and so on. Let's hit create. Every resource in Azure needs to have a subscription and a resource group. Let's give it a name, AdventureWorks, and we need to give it a server. Let's create one new. The server is where you configure the backup, authentication methods. Let's select Enter ID only authentication. It is the most secure. Let's give it a name. It has requirements, you see. The server name needs to be unique in Azure. Let's hit OK. So we want to use a single instance, not a elastic pool. It is for development, but it can be for production. This is just a demo. And the redundancy will choose 3 copies on the same region. locally redundant backup storage. We can connect to the database only if we open the database. So by default, we do not have any access, opposite to what you get with a storage account. This is normally closed. We will enable the public endpoint for us to interact with the database. So hit yes for Azure services and yes for my current IP address. There it is. Under security, the best option is to enable the Microsoft Defender for SQL. For SQL, we don't need to enable that now, but you could. You can start for free. You have 30 days trial. This database is empty, but for the demo, it will be better if it is using a sample set. So let's use that. Hit OK. And create. First, it will verify that our options are valid. Then it will deploy it. It will take a minute. So it is deploying both the server and the instance. This is not real server. It is the configuration portion of the instance. So it was accepted and deployed. Let's go to the resource. We will use this feature to query the database later. If the status is online, you can see the server name, .database.windows.net, and it is on OS 2. You will select the region that is closer to you. Let's query. We could potentially use a local account. We are not going that path. It is insecure. So we will use a Enter ID account instead. We'll run a query. This is SQL query on the table that was populated here. So this is sample data. So let's select from sales, product, hit run. And you can see it is giving me the database, contents, sales, and product. If you go to the right, you can see it has all the columns. Let's filter this view. We only need a few columns, so let's be more specific. Product ID, name, list price, product category. From the sales, product, that's fine. So only those categories. Perfect. We only have those 4 columns now: product ID, name, list price, and category. That saves some time, right? Instead of downloading the full thing, we're selecting the only portion that we need. You can also do a join. Let's remove this. And we can run the inner join here. And you can see how it works. You just run the query in the editor. Normally what you will do, you will connect that to a real application and interact in real world with real data. In this case, we run just a query within the tool to show you the capabilities right there. Let's confirm your understanding before we wrap up this section. First one, which deployment option offers the best compatibility when migrating an existing SQL Server on-premises solution? Take a moment to think. The correct answer is Azure SQL Managed Instance because it provides the highest alignment with the SQL Server engine used on premises. Let's move to the second question. Which of the following statements is true about Azure SQL Database? The correct answer is that most database maintenance tasks are automated. Azure SQL Database is fully managed platform as a service offering, so tasks like backups, patching, and monitoring happen for you. And the final question, which database service is the simplest option for migrating a LAMP application to Azure? Take a moment to think. The correct answer is Azure Database for MySQL, since it provides a managed MySQL engine that aligns naturally with LAMP applications. Great work through those. These questions will help you and reinforce why Azure provides multiple relational database options, each serving different needs, depending on compatibility requirements and the types of applications you are supporting. This brings us to the end of the session. We covered the essential ideas behind relational data in Azure. It introduced transactional data scenarios and explained how relational database organize data using tables, rows, relationships. This session covered Azure SQL Database, Azure SQL Managed Instance, and SQL Server on Azure Virtual Machines, with emphasis on recognizing when each option is appropriate rather than how to configure them. This concludes the session. We hope you'll join us as we journey through this course. We encourage you to watch other videos in this course or search out your next favorite topic on Microsoft Learn at aka.ms/learn.